Okay, in this chapter we're going to talk about carbohydrates. And the first part of that is just brushing on the structures and a little bit of the nomenclature. So we're going to compare aldoses and ketoses, enantiomers and diastereomers, stereochemistry is DL or RS, predict and draw the formation of ring structures from a linear sugar. Okay, so diving right in, the names of carbohydrates. How do you tell something's a carbohydrate? The name is going to end in OSE, O-S-E. That's a really great indicator that you're working with a carbohydrate, you're working with a sugar. Okay, so when we're talking aldoses versus ketoses, this OSE tells you it's a sugar. The ald and keto tell you the functional group of the sugar. Okay, so the aldoses have an aldehyde as part of their structure, CH2OH. Okay, so here's our example of an aldose, because you can see the aldehyde right there. As you would expect, the ketoses have a ketone, CH2OH. So this would be an example of a ketose. Okay, and if we want to get really technical, we can call this an aldotriose. So we see aldo, meaning it's an aldose. Tri is the number of carbons, 1, 2, 3, and ose means it's a carbohydrate. We can also call this a ketotriose for the same reasons. Ketone, 3 carbons, carbohydrate. Or we can get really specific and call these by their actual names. This is glyceraldehyde, and this is dihydroxyacetone. Okay, but then in naming we can get even more specific, because if you think about the structure here, I can draw it a different way too. I'm just showing you for an example, CH2OH. What if this hydroxyl group on this chiral carbon, chiral meaning it has 4 different attachments to it, this is the only chiral carbon on this molecule, what if it points this way? Okay, this would also be glyceraldehyde. These two have the exact same chemical formula. If you don't believe me, take a moment and draw it out, that these two have the exact same chemical formula, but their attachments are different. These are actually mirror images that are not superimposable. Because remember, these are Fisher projections. So these have stereochemistry that's coming out and hugging you, because Fisher projections really love you. They're so nice. Gotta love Fisher projections. So even though these are mirror images, if you tried to align them, it would not happen. And you can pull out models and test this for yourself. So that's what makes them enantiomers, non-superimposable mirror images. Okay, and we have ways of distinguishing the different enantiomers in carbohydrates based on the location, the position of the hydroxyl group on the bottommost chiral carbon. So you always put the aldehyde group at the top and the CH2OH at the bottom, and then the next carbon up is the last chiral carbon, and if the hydroxyl group is pointed to the right, like this one, it's to, as you're looking at it, it's to your right hand, then this would actually be D-glyceraldehyde. Most of the sugars in nature are D sugars. The bottom carbon has a hydroxyl group that points to the right. There are also some L sugars, so D is for dextro, L is for left, where the hydroxyl group points to the left. So that would make this L glyceraldehyde. Okay, so that's the difference between D and L. This designation goes over the entire molecule. This whole molecule is called D-glyceraldehyde. this whole molecule is called L-glyceraldehyde. And that's different than R and S. Okay. So R and S is based on priority on a single chiral carbon. So each carbon that is chiral has 4 different attachments. You can assign that carbon as designated R or S, and that's really based on the priorities of what's attached to it. So if you remember from organic chemistry, the first step is to probably make a model and put the lowest priority all the way at the bottom, so the farthest away from you. So the lowest priority is almost always H, so put that towards the back. So that's what this line means, going away. Then you order the rest based on the priorities shown here. So this hydroxyl group is going to be priority 1, followed by CHO is priority 2, followed by CH2OH is priority 3. So we've got 1, 2, 3, and this hydrogen's the lowest priority, priority 4. Okay, so then you just look at what the priorities are, and if it goes counterclockwise like this, then this carbon is S, or sinistro. If the priorities go, oh shoot, I messed this up. Pause. Okay, all better. That was accidentally the same configuration as over here. So if the priorities then go clockwise, like so, then that designation for that chiral carbon is R. So that's the difference between D and L and S and R. S and R are per carbon, D and L is for the entire molecule. They're definitely different. Okay, so thinking about sugars, we've kind of got one more problem when that I already talked about enantiomers. I'm also going to talk about diastereomers now. So diastereomers, huge problem in carbohydrates. These are compounds that have the same formula and a completely different rearrangement of the hydroxyl group. Different arrangement. So that gives them different chemical properties, even though they have the exact same chemical formula. So I'm going to look at some aldo tetroses here, just to illustrate this example. CH2OH, HH. Next one, 2, 3, 4. Top and the bottom are the same, aldehyde, but H, OH, H. Okay, first off, both of these are D configuration because the bottom hydroxyl, the one that's attached to the bottom chiral carbon, is pointing to the right. So both of these are D. And if we look one up, these are not mirror images either. They're not identical, they're not mirror images, they have a different arrangement of these hydroxyl groups that give them different formulas and different properties. They have completely different names. So this is very, very common in carbohydrates. There's many different forms of pentoses and hexoses and tetroses, and they all have different names, and the nomenclature kind of makes no sense. It's one of those things that you have to memorize if that would be required for your exam, which it will not be. Okay, and then the last thing I want to talk about is the stability of particularly pentoses and hexoses in water. So we draw it in Fisher projection here with, and it looks nice and stable, right? Until you realize that each one of these hydroxyl groups is a nucleophile, and this carbon is a great electrophile. And when we move far enough away, we can overcome the steric hindrance in order to have a nucleophilic attack on this carbon. The electrons from this double bond can then be used to pick up a proton in solution, and we can end up with a cyclic form. So this mostly happens for the 5 carbon sugars and the 6 carbon sugars. But this gives us another problem as well, which I'm going to show you here. So when we draw this as a Fisher projection, I'm just going to use dashes for the OHs because I don't want to waste all that time. So this hydroxyl group, is this going to point to the right or is it going to point to the left? Because this carbon is still chiral. And the answer is sometimes it's going to point to the right and sometimes it's going to point to the left. And that's another distinction that we have to make. And that's the distinction of alpha versus beta in these ring structures. One second, so you can see left, right, right. Okay, and so when it points to the right, we've got the alpha, and this would actually be ribofuranose because it's a 5-membered ring, and this would be the beta ribofuranose. So this distinction is important for the ring structures, alpha versus beta. And that's because this carbon is called the anomeric carbon. This is a carbon that previously housed the ketone. And this hydroxyl group, when it is formed, will either be to the right or be to the left when it picks up that proton from the solution. Okay, so these are both Fisher projections of the ribofuranose, and sometimes the alpha and beta is easier to understand if we draw it as a Haworth projection. Okay, and it's really easy to adapt a Fisher projection to a Haworth projection. So first off, you count the number of carbons, 1, 2, 3, 4, and then this oxygen makes a 5-membered ring. So you put the oxygen on the top, 1, 2, 3, 4. We can do that for both of them. 3, 4. Okay. And then everything that points, every hydroxyl that points to the right is going to be down. And you might want to number your carbons, 2, 3, 4, 5, just to keep track of them. So this is going to be carbon 1, 2, 3, 4, and carbon 5 is attached to carbon 4. HO, H2C. Okay, we get the same thing here. CH2OH. Okay. And this carbon, remember, is not chiral, so it doesn't really it doesn't really matter where these hydrogens are, just that they're there. Okay, so now, and everything to the right is pointing down. So the alpha hydroxyl group would be pointing down, C2 hydroxyl group is pointing down, C3 hydroxyl group is pointing down, and then C4, this is attached to that oxygen. Okay, one more. 1, 2, 3, 4. Here, this is 1, 2, 3, 4, and this is carbon 5 at the bottom there. Okay, so here it's pointing to the left. So the left is up. This hydroxyl group, we switch back colors, is going to point up. This one was pointing down. And that is really the difference between the alpha furanose, the alpha would point down, the beta one would point up. Everything else is the same. So if you're given a Haworth projection, really super easy. If you're given a Fisher projection, you can either memorize or you can convert that into a Haworth projection in order to answer the question, what's alpha, what's beta. And then, just to make this problem a little bit more interesting, these are all the furanose forms. There's nothing stopping this carbon, this hydroxyl group, which is also a nucleophile, from attacking that same carbon as well and forming pyranose rings. So a pyranose ring would be a 6-membered ring. So we could get a form that looks like this. This would be down OH, and then down, down, down. CH2 over here. And so this would be the alpha form, or we could get the beta form. And CH2 is right there. We do 1, 2, 3, 4, 5. And then this makes member 6. 1, 2, 3, 4, 5. Okay. Same on both. 2, 3, 4, 5. Okay. So this, again, this would be the alpha, this would be the beta ribopyranose forms. And then, as you can imagine, the same sort of situation could occur in 5-member, 6-member, or 5-carbon, 6-carbon ketoses as well. But I'm not going to bother to draw that out.